Alright, I want to give a little bit of a video to help with implicit differentiation. So, apologize for my voice. It's a little scratchy today. And I don't have any sort of special slides prepared in advance. So implicit differentiation starts with the idea of using the chain rule. So I want to just illustrate a few examples of the chain rule in action. So for example, if I told you that we knew what y was, if we knew that y was equal to something like x squared plus 1, and I wanted to find a derivative, for example, the derivative with respect to x of y squared. Well, if I thought about that, I have my function x squared plus 1 that I'm trying to square. And I would have to use the chain rule. So what I have to do is I would typically call this thing inside, maybe I'd call it u, and my derivative would be something like take the derivative with respect to u of u squared and then multiply by the derivative of u with respect to x. Now the silly thing is that I already have a name for my variable. I've already called it y. So there's no point in using u. Let's just use y. So our problem should be thought of in terms of y as first I take a derivative with respect to y of y squared, and then we'll multiply times the derivative of y with respect to x. Now the derivative of y squared with respect to y is 2y. The derivative of y with respect to x for our problem is the derivative of x squared plus 1. And that's 2x. So I get 2y times 2x. Or a final answer, 4xy. So in implicit differentiation, we don't know the actual formula. So if I had take the derivative with respect to x of y squared, I don't actually know what y is this time. And so I'm going to do the same thing I did before. We take a derivative with respect to y of y squared, but I have to multiply it by a derivative of y with respect to x. So I get 2y, that's the derivative of y squared with respect to y, times dy dx. And dy dx this time is a variable. Dy dx is a variable with no formula. So let's do some more examples. I could be asking, how would I take a derivative of x squared times y squared? Well, I look at this and I say, oh, that's formed as a product. And so I have to use the product rule. Take a derivative of x squared, multiply it by y squared, and we add x squared, multiply it by the derivative of y squared. The derivative of x squared, we know, is 2x. So we get 2x times y squared plus x squared times the derivative of y. But again, the derivative of y squared. Again, I have to take a derivative with respect to y, and I get 2y times dy dx. And so my final answer is 2xy squared plus 2x squared y times the third variable dy dx. Now, I should warn, missing this product is one of the students' most common mistakes. So implicit differentiation is used to find the slope, the derivative, dy dx, when y is given by an equation that does not solve for y. So as an example, let's review the one we did in class. X squared minus 2xy plus 3y squared equals 4. We started this one, but we didn't finish, so I'll use this as an example here as well. The graph of this equation is an ellipse, so we can see, for example, that y is actually not even a function of x. It fails the vertical line test. But we can still find slopes. The idea of implicit differentiation is to take an equation which has two parts. There's a formula on the left, and there's a formula on the right. In this case, the formula on the right is just a number, but it could be an actual formula that involves variables. The idea of implicit differentiation says if I take a derivative of the formula on the left, it has to equal the derivative of the formula on the right. And I can now use the tool of the chain rule to be able to calculate the derivatives in terms of x, y, and dy dx to get a new equation for my derivative. So, the derivative of x squared is 2x. The derivative of negative 2xy requires the product rule. So we need to subtract the derivative of 2x times y, and I need to subtract the derivative of y times 2x. The third term involves a function of y, 3y squared, and so I need to use the chain rule. Plus the derivative with respect to y of 3y squared times dy dx. That is the derivative of the left side. The derivative of the right side is just 0 because the right formula was a constant. So let's compute all those derivatives. The derivative of 2x with respect to x is 2. So I get 2x minus 2y. The derivative of y with respect to x is our variable dy dx. The derivative of 3y squared is 6y, and the reason that we say 6y by itself, is because I'm actually taking the derivative with respect to my variable y. I've already included the chain rule factor. So now my goal is to solve for the derivative, which appears in two places. So what I'm going to do is I'm going to solve for that variable. I need to subtract 2x, I need to add 2y to both sides, and I'll factor out the common factor dy dx. I can now divide both sides by negative 2x plus 6y. And I have it. The derivative of y with respect to x is always found by taking the point x and y, plugging them into the formula negative 2x plus 2y all over negative 2x plus 6y. The question we asked in class, that I'd like to ask now and finish the problem is to say where the graph has horizontal tangents. The idea of horizontal tangents is to say that my slope equals 0. Our slope is given by derivative, so what we're really looking for is the derivative equals 0. But our derivative was given by the formula negative 2x plus 2y over negative 2x plus 6y. And so we can set that equal to 0 and solve. This is only going to be true if negative 2x plus 2y equals 0, the numerator. If I solve for y, I discover y equals x. This line corresponds to the line y equals x. I would be looking for these 2 points where the line y equals x crosses the ellipse. How would I do that? Well, I have 2 equations. I have an equation for the graph, and I have an equation for the slope. Our goal is to find the intersection. And so we need to solve these equations simultaneously. What we'll do is we'll take y equals x and we'll substitute into the other equation. So everywhere we see y, we'll replace it with x. So what we're really doing is we're looking at specific points of interest, the points where we have horizontal tangents. At those points, y equals x, and our equation can be replaced by x squared minus 2 times x times y, which is x, plus 3y squared, which is 3x squared, equals 4. This is not true for all the points on the graph. This is only true for the points where I am at my horizontal slope. So if I simplify this, I have, there's 2x squared that's negative, 4x squared that are positive. I get 2x squared equals 4, x squared equals 2. I find 2 points, x equals plus or minus the square root of 2. Now, to get the y values, I remember at the points of interest, y equals x. And so my 2 points with horizontal tangents are at the square root of 2, the square root of 2, and negative square root of 2, negative square root of 2. And that's how implicit differentiation works.